Well, welcome to this webinar about Masters in Astronomy and Astrophysics at ANU. The presentation is live at the moment. It will also be, my component of the presentation will be recorded, and then we'll have some questions and answers after I've gone through the main part of the slides. So, and feel free to interrupt at any time you'd like, because there is a small group here today. So first, a little bit of a history of the Research School of Astronomy and Astrophysics, or RSAA for short. And we're a part of ANU today, but our history goes back quite a long way. We were originally established in 1924, which was well before ANU. At that time, it was just as the Commonwealth Solar Observatory. Became part of the ANU basically when it opened in 1954. We've got the major observatory, the Siding Spring Observatory, started in 1960, Australia's biggest observatory. And we are usually ranked in sort of roughly the top 10 institutes in the world in astronomy and space science. It comes and goes. And we've had major prizes for many of our key staff members, including the Nobel Prize for Physics for Brian Schmidt. So where are we? So there's the Mount Stromlo Observatory is just outside of Canberra. So it's about 15 minutes drive from downtown Canberra. There's a bus up and down each day. And we also have the observatory in Coonabarabran, which is a 7-hour drive away. Most of the telescopes are operated remotely. And here's a picture of Coonabarabran down the bottom here. The School of Astronomy and Astrophysics is big enough that we have quite a broad range of research topics that go on up here. So there's stellar and planetary astronomy, which is more or less what I'm part of. There's cosmology. There's galactic archaeology. So this is sort of the boundary between stellar and galactic physics, where stars are used as probes for the history of our galaxy. There's black holes and other sort of exotic phenomena. And there's a lot of work on astronomical instrumentation and space technologies. So some pretty pictures to start off with. Here's the sort of thing that I work on, both with people at Stromlo, where I am, and down in Earth Sciences on the main campus at Acton, in the center of Canberra. Answering questions of how planets, both terrestrial and giant planets, form and how their planetary systems evolve. There's plenty of people like Naomi McClure-Griffiths down in the bottom right who work on our galaxy. Naomi in particular works on the gas, the hydrogen gas more than other types of gas, but the gas that is turbulent and forms the stars in the galaxy. And she uses radio telescopes around the world for this. Australia is, of course, a leader in radio astronomy. And the telescope up the top there is the picture of the AAT. That's the largest telescope in Australia, which is at the ANU site of Siding Spring Observatory. We also, of course, use many satellites in the modern world. The public data from the Gaia satellite, which is up in the top right there, is extremely useful for studying the galaxy currently this year. So this is the sort of image that you think about when you think of cosmology, one of the Hubble deep field images, where you see back to the very earliest galaxies that formed. The main sort of resource we have for studying cosmology is our imaging telescope, SkyMapper, also at Siding Spring Observatory, as well as all the international telescopes around the world. SkyMapper telescopes maps the entire southern sky. So what sort of evidence is there that we have some great people that do good work up here? So there's, of course, Brian Schmidt's Nobel Prize. There's many prizes from Ken Freeman, including the Prime Minister's Prize for Science. We've had what's called the Australian Research Council Fellowships. Many of our staff members have received them. the moment, Lisa Cooley, and in the past, Brian Smith and Martin Asplund. And the next level of fellowship down, ARC Future Fellows, we have many of them today. In the past, I'm Mike Ireland, have had one of them in the past as well. And we're, of course, got many members in the Australian Academy of Science and also internationally. So here's a picture of Mount Stromlo down the bottom. The big building here is our instrumentation building mostly. This is where we build instruments for large telescopes. So there's, in addition to the telescopes in Australia, Australia is now a partner of the European Southern Observatory. We have access to these telescopes and we're building instruments for ESO as well. We're also a significant player in the Giant Magellan Telescope. As part of sort of looking towards the future, we have an active group doing space test and design of new missions. Australia now has a small space agency itself. One of our bigger facilities in the instrumentation group is this thermal vacuum chamber called the Wombat, or we just call it the SSF, the Space Simulation Facility. And yeah, there's many other space-related test and assembly sort of equipment in our instrumentation group. So like I said before, please feel free to interrupt at any time. I believe you can unmute yourself. If you would like, you can also put questions into the Zoom chat. So the modern world of astrophysics is very collaborative. We have many ongoing partnerships and collaborations throughout the world. So here's some of them listed here. I can answer more questions on that if anyone's interested. Where do people from ANU go to? So astrophysics is very international, and we've had graduates from ANU going around the world for 50 years, for more than 50 years now. And they're employed around the world. Typically, students that do well will go to some of the top institutes in Europe or USA, because they're the powerhouses that have been historically in astrophysics. And so certainly master's students have gone on to do PhDs at Max Planck Institutes, like Cambridge, Caltech, etc. So what do you do if you start with a master's in astrophysics? Well, a traditional astrophysicist, the standard astrophysics, sort of how do I become a world famous astrophysicist career path? The path starts and then during a PhD, and then in terms of employment begins after a PhD. Increasingly, however, many students are getting jobs in many other areas, particular data science, specialist companies that consult on a range of society topics. Basically anything where there's a combination of modeling, thinking outside the box, computing. That's where astrophysics graduates tend to be sought after. Of course, within Australia, there's a lot of emphasis on geoscience, and we certainly have graduates that have gone into this field as well. So it's not just astrophysics. And the reason that the students do get jobs in all sorts of places is because astrophysics involves a broad set of skills for tackling complex problems, and employers are increasingly realizing this, certainly in Australia. So in terms of what would actually happen in a master's program here, so the first part of the master's program for many international students in particular, or from students that didn't do astrophysics in undergrad, is to sort of catch up on the most senior astrophysics courses that we have in our undergrad degree. So there's 3 key subjects. There's galaxies and cosmology, there's stars, and there's astrophysical processes. So there was someone that did a thumbs up. If you'd like to speak, feel free, or type into the chat window in Zoom. So these courses have, in particular, 2 of them have already approved undergraduate and master's versions. There's galaxies and cosmology, and there's stars. These are the fundamentals of many of the more advanced astrophysics topics. There's also, so these courses are all taken at our main campus, just near the centre of Canberra. And they cover, and the stars course covers everything from the evolution of stars, the structure of stars, what the way a stellar atmosphere works. And it studies this both from a theoretical, a practical, and a numerical perspective. The Galaxies and Cosmology course studies both how our Milky Way is put together, and are not very much on that topic, more about galaxies throughout the universe, how they evolve, and how they fit into the story of the universe as a whole, which is cosmology, and has a lot of complex concepts to understand about the way space-time works in the universe as a whole. We also have a course on astrophysical processes. So this is the physics of astrophysics, and we'll be applying to make that a master's course as well from next year. And this is about how radiation interacts with matter, and how matter interacts with itself through things like shocks and hydrodynamics. Some of the other courses in masters can also be taken on the main campus. The 3 that I think are most relevant that many students take is scientific computing, particularly people don't have a background in MATLAB or Python to solve numerical problems. Optical instrumentation, which was a course also taken by photonics students, and planetary science. And our 2 master's programs also include science and society courses, which could potentially include an internship, for example, at our observatory at Siding Spring. So at the more advanced level, we have what's called the 8,000 level courses. And at the moment we have 7 that are definitely going to be offered, and we're looking into an 8th. 2 of these are going to be every year, and the others oscillate. And these are sort of the more advanced courses. Observational Techniques is about how you both apply for time on the world's largest telescopes, and once you get the data, how to analyze that to write research papers. Astronomical Computing is about a range of topics about both the numerical and data science methods we use in astronomy. And that's really important in the modern world. And the other 5 courses are high-level courses in key topics throughout astrophysics. And I'm happy to answer any questions people have on them once I'm finished. So all these courses, both at undergrad and especially at the higher level, at the 6,000 level, which is the more junior master's course, and the 8,000 level, the more senior courses, they really focus on problem solving. So there's quite small classes and interactive teaching styles. So there's often only 5 students in the 8,000 level courses, sometimes up to 15, but they're typically small groups where you're given quite difficult problems which you have to discuss as a class to solve. Some of the problems are numerical, so you end up both needing to use the skills that you've learnt in courses like the scientific computing course, and also develop new numerical skills. And that's very important to the way we teach. It's about practically solving the problems of astrophysics. So if you look up masters at ANU in astrophysics, there's 3 masters that you can still find online, but there's only 2 that are actually current for next year onwards, and that's the Masters of Science in Astronomy and Astrophysics, one with a bracket advanced and one without that. In the advanced version, which I'll start first, it's 48 units is dedicated to a research project. So this is twice the size of an honours undergraduate research project in Australia, and is designed to put students in the best possible place for starting a PhD. The combination of a master's bracket advanced and a PhD is a training in astrophysics that's as good as anywhere else in the world. For example, the top schools in the United States, they have the similar sort of structure, with the first 2 years of a 5-year PhD program being 1 year full-time research and 1 year full-time coursework, roughly. This model is also called the Bologna model within Europe. If you wanted to see what sort of research projects you can do, there's a potential projects page at our main webpage for RSAA. And a little bit more about this advanced masters and why there's two streams. For the advanced masters to be a pathway to a PhD, students really have to be performing at the level where there's a reasonable chance of them getting that PhD scholarship afterwards, for the pure 3-year research PhD afterwards. So this is a competitive process with a limited number each year, but typically there's sort of this thing called an honors class 1 on 80% mark that enables students to usually get a scholarship, and 85% where students would almost always get a scholarship. This sounds like very high marks, but high marks are certainly not uncommon, because these are more or less normalized to undergraduate marks. And I can explain what I mean by that if people want to ask. And so because of those sort of marks that are needed to get into the PhD program, and that's what the master's is, the advanced version is supposed to be a pathway to a PhD, there is a requirement that people need to have an average mark of 70% to transfer into the advanced stream. Or to remain in it after the first semester of the advanced version. Okay, so where to find more information about the programs? So all the information is at this website called programsandcourses.anu.edu.au. And I've got the 2 links here. It's VSC, strange codes, VSCAA and NSCAA. Yeah. And I can, if anyone has questions, I can open those web page out and I can go through whatever people want. So someone just left and sent me a message. If anyone wants to send other messages, please do, or just call out, and that's okay. So the admissions, how do you get into this program? It's all at that website called Programs and Courses. The admissions are generally handled centrally at ANU. So what we assess at Stromlo, at the Research School of Astronomy and Astrophysics, is the cognate background. Of course, this is a bit unusual for the advanced versions. I'll go through what this really means. You have to have a bachelor's degree with a minimum GPA of 5.5. So 5.5 is sort of roughly half credits and half distinctions at ANU. And you have to have at least 8 courses, that's ANU equivalent courses, in a cognate discipline. So cognate discipline typically means physics and mathematics subjects, but there's the full list at the Programs and Courses website. And for the advanced version also, there's this completion of Astro 3005 equivalent, which is basically an undergraduate research topic. Now, if someone doesn't have that undergraduate research experience, it's still okay and they can get into our program. But the way that we've set it up is that a student would have to enroll in the non-advanced version first and then transfer to the advanced version. Another very important point I should make is that which I don't actually have here in the slide, is that the advanced version also has scholarships. And there's not scholarships for the full fees, but they are scholarships that help out. It's $10,000 per year. And there's multiple scholarships available. Again, they're competitive, but it's only for the advanced version of the course. And people can also get a scholarship at the moment halfway through a degree. So if someone transfers into the advanced version, they're still eligible to apply for this scholarship, which again, it does not cover the fees. It's just a scholarship, an additional scholarship funded by our research school.